Hello everyone, I'm Leonardo. I'm a PhD candidate in applied math and computational science, and I'm here today to talk to you about how to know what you don't know. And I want to begin by asking each of you a question. Have you ever been absolutely sure about something and then turned out to be completely wrong? If so, you're not alone. This is actually a very common phenomenon of the human mind, and psychologists have studied it extensively. You might have even heard of the Dunning-Kruger effect, which states that people with little knowledge about a subject tend to be overconfident in their abilities, while experts are often more cautious. This mismatch between true and perceived ability is often most stark when we know very little, something people even call peak of Mount Stupid. Luckily, with AI being on the rise, we can rest assured that machines won't be susceptible to the same pitfalls as we silly humans, right? Well, it's not so simple. Machine learning models suffer from a similar problem. They make predictions, but they rarely tell us how confident they are, leading to risks when deploying them in the real world. This makes a big difference for high-consequence scenarios, such as self-driving cars and medical diagnosis, where a mistake can literally mean the difference between life and death. And don't get me wrong, machine learning models are often great at making predictions. But without knowing uncertainty, they can be dangerously overconfident. We need more than just answers from AI. We need to know how much we can trust those answers. In other words, we need AI to be able to quantify how confident they are in their answers. Instead of having models output a single prediction, like we see here, outputting the number 0 without any added information, we should get a range of possibilities that describe different possible outcomes. In this graph, the x-axis indicates values and the y-axis indicates frequency. This also helps us distinguish between scenarios where we have high uncertainty, with like the one shown here, from scenarios where we have lower uncertainty, as can be seen in the bottom graph, where there's a narrower range of possible values concentrated more closely around 0. This is important because we don't always have all the information required to make deterministic predictions. In addition, many problems in nature are inherently random. On the left, you can see that these balls can fall in many different ways, so it's impossible to account for a range of possible outcomes. For applications such as operating a nuclear power plant, for example, this can help us distinguish between scenarios where we have safe operation versus scenarios that could lead to catastrophic system collapses. The difference between a single prediction and one with uncertainty is stark. The reactor won't fail versus there's a 2% chance that it will. Two statements, two very different decisions. So hopefully by now I've convinced you that quantifying uncertainty is important. But how should you go about it? Well, if you're anything like me, when I come across an ethical dilemma and I want to gauge whether my decision is correct, I ask my friends. And the technical term, hearing a different opinion can help you consider different possibilities. And in machine learning, the technical term for this is model ensembling. Model ensembling consists of having different models make independent predictions instead of relying on a single model. It's been used for decades in high-stake fields such as hurricane forecasting. Here's an ensemble forecast of Hurricane Ian from 2022. Most models show it passing through Florida into Georgia, but some of them predict Alabama or instead the Carolinas. This spread reveals our uncertainty. If the predictions are close to each other, there's low uncertainty. But if they're far from each other, we know there's high uncertainty. But what if all models share the same bias? If they all predict Ian will go east, they will all be confidently wrong. A hive mind where all models are the same leads to overconfidence. If all models are too similar, they reinforce each other's mistakes. But with diversity, errors in opposite directions average out, making predictions more reliable. This is actually something that can be proven mathematically. In 2008, Scott Page published a paper showing that the error of an ensemble is equal to the individual error and the average error an individual model makes minus the diversity in predictions. This means that if we want to decrease our error, we need to increase diversity. This, in order to make good predictions and have reasonable uncertainty measures, we need diversity in predictions. And this isn't a feel-good, hand-wavy slogan, it's a mathematical fact. So much so that researchers have spent decades building methods to ensure statistical diversity in ensembles. There are way more of them than I can even begin to describe here, and they show in practice that diversity leads to better decision making. And once we have good uncertainty measures and know where our knowledge is weakest, that is, where uncertainty is greatest, the smartest thing to do is to go out and learn more. And I would argue that this is the essence of intelligent decision making. Not just making predictions, but seeking the right questions to ask. This leads to a virtuous cycle where we can train a model using available data, then we identify our most uncertain predictions and conduct experiments to resolve them. We then add these new points to our data set and retrain with the new insights. Each step refines our understanding, making predictions stronger over time. This actually describes a lot of the research that I do. For example, a project I work on consists of designing soft robots made of flexible rubber instead of metal, enabling safer human-robot interactions, like assisting bedridden patients in hospital beds. This field is still new, and we need to understand how to design these robots and their physical properties. Reliable models not only predict behavior, but also tell us how confident we should be in those predictions, guiding experiments more effectively. Here you see one of these robots lifting a mannequin leg. On the right, I plot real experimental data in green along with predictions in gray of an ensemble of neural networks that I trained to predict the behavior. As you can see, the predictions are extremely close to the real experiments, and they generalize well to the trend we see in the data. Another project I have is a partnership with Samsung on microchip manufacturing. Making chips is a complicated, multi-stage process with many possible points of failure. As such, the proportion of chips successfully made, also known as yield, can be as low as 50%. In this project, we hope to determine the best parameters for this complex manufacturing process as to obtain the highest possible yield. And preliminary results on artificial data tell us that this is indeed possible. In this histogram of objective scores for manufacturing parameters, we see the best value in the original data set provided by Samsung is 250. By leveraging a neural network with built-in uncertainty quantification, we can guide experiments in an efficient way, balancing exploration and exploitation. Overall, we're able to find an objective of 500 with only a small fraction of original experiments. So I promise to tell you how to know what you don't know. First, you should embrace uncertainty because it will be there whether you want it or not. Then, you should encourage diversity because hive minds don't make the best decisions. And finally, you should act in your ignorance. Collect new evidence based on the things you don't know. If we want safe, reliable AI, we need to stop asking for just answers and start asking, how sure are you? Thank you very much.